Suppose that the distance of fly balls hit to the outfield in baseball is normally distributed with a mean of 295 feet and a standard deviation of 38 feet. So again, this question is asking us two different things. For part one, we want to know 26% of fly balls are hit further than what distance. So here we're looking at one fly ball at a time. For part two, the question's a little bit different. Instead of looking at just one fly ball at a time, we're considering a random sample of 97 fly balls. And we want to look at 26% of possible samples of 97 fly balls have an average travel distance greater than what? Okay, so in part one, we are again looking at just one at a time, just like we have done in the past couple sections. In number two, we're looking at a sample of 97 fly balls, which means we'll need the central limit theorem to be able to consider the sampling distribution. Okay, so let's start with part one. It's a normal distribution, and the problem itself tells us if we're looking at fly balls generally, the population of fly balls, the mean is 295, and the standard deviation is 38 feet. So we want to find the z-score here. Now, notice what the problem's asking. It's saying, for part one, it's saying that the probability that a fly ball is hit further than some distance is 26%. Okay? So the problem is giving us the probability. It wants us to find a particular value. Remember, when we have a probability and we want to find a particular value, we start by using the Q-norm function, and then we find that particular value using the formula x equals the mean plus z times the standard deviation. Okay, so that's what we're going to do here. So the first thing we need is to find the z-score associated with that 0.26 using the Q-norm function. The z-score, so that the probability that a randomly chosen z-value will be bigger than that z-score, is 26%, or 0.26. Okay? So I'll use Q-norm. This is going to be my z-value. Q-norm. I'm going to plug in my probability, which was 0.26. Okay? Now the problem is that just like with the p-norm function, this assumes that we want a probability in the lower tail. That's not what this is telling us, right? Here, we're expecting a probability in the upper tail. If we draw this out, the mean is 295. We want some value here so that the probability that we get something bigger than that value is 0.26. Okay, so that's a probability in the upper tail. So whenever we are dealing with a probability in the upper tail, we could convert it to a probability in the lower tail by 1 minus that. Okay, that's taking the whole probability under the curve, 100% of the probability. If I subtract the 26% in the upper tail, what's left is what's in the lower tail. And that way, this Q-norm function has a probability in the lower tail. Okay? So the z-score is 0.64334454. Okay? That means that the probability that z is greater than 0.6433454 is 0.26. Okay, now we need to, now that we have the z-score, we need to apply this formula here so that we can find the particular value we're interested in. Okay, so that's 295 is the mean for this particular distribution, plus my z-score, times the standard deviation, which for the population is 38. Okay, so the particular value I'm looking for is 295 plus the z-score I calculated times 38, the standard deviation. And we get 319. Okay, so that means 26% of all fly balls in baseball travel further than 319.4471 feet. Okay, that's this mystery value here that we've just found. Okay, let's look at part 2. It's similar, but now we're looking at a sample of 97 fly balls. Okay, so in order to understand the distribution we're dealing with, which would be the sampling distribution of all sample means, we need to use the central limit theorem. Remember, the central limit theorem says the sampling distribution for any population is normally distributed, where the mean of the sampling distribution is the same as the mean of the population. And the standard deviation of the sampling distribution, which we call standard error, is the standard deviation of the population divided by square root of the sample sizes that we're looking at. Okay? So, because the mean of the sampling distribution is the same as the mean of the population, and the mean of the population was 295, this is still 295. Okay? But to calculate the standard error of the sampling distribution, we're going to take the standard deviation of the population and divide by square root of the sample size. The standard deviation of the population is 38, and we're looking at 97 fly balls at a time, so that's our sample size. So our standard error is 38 divided by square root of the sample size, and we're looking at 97 fly balls at a time. That's our sample. And so the standard error is 3.858315. Okay? So because we're looking at this larger sample of fly balls, this is the distribution we are going to use for our calculations. What we want to do is we want to find the value so that 26% of samples of fly balls have an average travel distance greater than that value. So mathematically, that means we want the probability that a randomly chosen sample mean would be greater than this value, that the probability of that happening is 0.26. Okay? So just like before, we know the probability. We want to find a particular value, which in this case, because we're dealing with a sampling distribution of the sample means, the particular value is represented by x bar. To find that, we need to first find our z-score using the q-norm function. And then our formula to find that actual x bar. Remember, the symbols are going to change here, but it's still the mean plus the z-score times the standard deviation or standard error. Okay, just make sure you're using the correct symbols for the distribution you're working with. Okay, so let's start with that q-norm function. It's going to be q norm p equals 1 minus 0.26, because that 0.26 here, it represents the area in the upper tail, right? Since we are only allowed to put values, the probabilities that are in the lower tail here, to convert this upper tail probability to a lower tail probability, we do 1 minus 0.26. That would leave us with this bit to the left of that mystery value. Okay? So we get a z-score of, whoops, let's take that 2 out, 0.6433454. Notice, interestingly, the z-scores here are the same. That really isn't surprising yet. because we haven't used the fact that we're dealing with the sampling distribution instead of just the population distribution that we started with. Okay, all we've done is we've converted probability to a z-score. For both of these problems, the probability was 26% or 0.26. Okay, so it's not surprising that we're getting the same z-score because we're starting with that same probability. We're starting with that same probability and getting to that z. Okay, now that we have that z-score, now we want to use this formula to actually find the particular average that we're interested in. So that average is 295. I think I wrote 395 here. 295. So that's 295 plus the z-score we calculated, that's 0.6433454, times our standard error, which we found was 3.858315. I'm not going to write all that down. I'll just write sigma over root n. So in our calculator, that looks like our particular value is an x bar. It's a mean because of the distribution we're working with. The population mean, 295, plus the z-score times the standard error. We get 297.4822. Notice again that the population value here, the particular value for the population when we're looking at every individual fly ball, is higher than we're looking at a sample. That makes sense. If we're looking at balls one by one, a fair number might fly further than 319 feet, right? But if we're looking at a large sample of fly balls, that means some of those fly balls in our sample, they'll likely not travel very far. Some of them might be crazy home runs, but they kind of even out, right? So the average is likely to be much closer to the actual population mean.